Okay. So trying to think if, I don't know if, have you guys had any multivariable calculus beyond just like the first time you saw partial derivatives in the class and anything like that? Okay. So I don't know if people do this definition anywhere else, but the main reference for this is Spivak. And this is just, when I say multivariable calculus, I'm only doing differential calculus. But of course, there's a whole thing about integral calculus in multiple dimensions to think about as well. And Spivak's book also has this, but Spivak has a really nice tiny book called Calculus on Manifolds. It's small, it's 5 kind of small chapters, and it's really nice and readable and has really good exercises. So I highly recommend doing it. I'm only referencing chapter 2 here. So if all you read is chapter 2, I think you will be pretty good to go for some stuff. Not even the whole chapter 2 really. There's some stuff at the end. Actually, I think one proof of some big theorem might have a mistake in it, but the definitions and important stuff at the beginning and like in the first half are all correct and very good. Okay. So this is just for differential calculus. Okay. All right, so let's talk about the derivative in multiple dimensions, right? So I'm going to assume that we know the derivative in one variable calculus, like Calc 1. And I think there's nothing wrong with that definition, right? So let's start with a function from R to R. So a single variable function, meaning you only have one variable going in, and then it's a scalar function, meaning you only have one variable coming out, right? This is as opposed to like a multivariable function where you have multiple inputs, and then a vector valued function is where you have multiple outputs, right? So something like from Rn to Rm would be a vector valued multivariable function, right? And those are the kinds of objects we dealt with in Calc 3. But in Calc 1, we just have these one variable scalar functions. So let's just really quickly define the derivative. This is familiar, hopefully, to everyone, that fix a point inside of R, then the derivative of f at a is just the number. If this limit exists, it's the number f prime of a, which is defined by the limit as h goes to 0 of this difference quotient, right? So we remember this definition. So we want to extend this definition to higher derivatives, but we need to change things around a little bit from this definition before we can generalize it immediately, right? So if we imagine, just before we go into this stuff, just look at this difference quotient and see if what would change if f was a function from Rn to Rm, right? Where n and m it's best if they are different here, right? But actually, it doesn't matter, but just n and m are not just one, right? Well, you can see that this bottom thing, h, is, has to live in the domain, right? Because we take like something like a plus h. That means a is in Rn. That means h also has to be in Rn. Right, so h is actually a vector in Rn. And then, so this bottom thing is actually a vector, so it doesn't make sense to divide by a vector. Right. And then at the numerator, right, we have f of something in Rn, right, f of a. This is the output, which is in Rm, right? So the numerator lives in an entirely different vector space, right, from the denominator. So it doesn't quite make sense to write down this thing exactly as it is. Right? It would be like this vector divided by this vector. So we need to change things in some other way. So I'm going to reformulate this equality. So originally we have, let's say f is differentiable at a, and let's say that this limit exists, just so we don't have to worry about it. Let's move over f prime of a to the other side, and we can agree that this equation is the same as this combined a difference quotient being equal to 0, right? So what I did was I just multiplied by h, took this number and multiplied it by h, and then put it into the fraction. Sorry, multiplied it and divided it by h, right? Okay, and then I'm just going to relabel this as lambda of h. It's a function on h. Okay, and it's a function which takes in like one number, which is h, and spits out lambda of h, and that is given by just f prime of a times h, right? And this is a linear function, right? In one variable, in this one variable to one variable case, the linear functions are just you multiply by a single number, right? A single fixed number. Right? If we wanted to rewrite this in terms of like matrices to make it clear that it's a linear function acting on a vector, right? Because all the linear functions correspond to matrices and matrix multiplication, right? This is just a 1-by-1 matrix multiplying a column 1 vector, right? So it is just another 1-by-1 matrix, but you want to think of this one as a vector and this one as a matrix in order to generalize to the next step properly, right? But so this is a 1-by-1 matrix with the entry depending on a. It's f prime of a. It's the derivative that we're more familiar with. Great. So this I'm going to think of as this linear function. This is an important linear function. And so what I want to look at is where f of a plus h minus this linear function divided by h, the limit of this goes to 0, right? Okay. So, well, this doesn't really solve the problem that I talked about before about like this thing is a vector and the numerator is also a different vector, right? But it does reformulate a little bit things in terms of linear maps. So that's kind of good. So, and also we have a limit equaling 0, and these are a little bit easier to deal with, which we'll see. So here's just an alternate definition of just a single variable derivative. So we could have at the beginning defined the derivative of a single variable scalar function to be this new formulation, which is just that this limit is now equal to 0. Okay. And the derivative is the linear map such that this is equal to 0. Okay. So a way of interpreting this is that this combined quantity, the sum of these two, is a linear approximation to f of a plus h, or it's a linear approximation to f close to a, right? Which is kind of what we want to get at with this derivative. And then whatever that slope of that line is, or the number that represents that linear function, is the derivative. Okay, so now if we want to work with multiple dimensions, we have to work around this vector problem. But since we've reformulated it in a way that it's like a limit of something goes to 0, or a limit of something is 0, we can take norms basically everywhere. And that's how we solve the vector problem, so that we're only working with real numbers at the end, right? But so if we have a function from Rn to Rm, so this is a multivariable function that is vector valued, then the derivative of f at a, now a is a vector inside of Rn, it's a position in this vector space. This is the linear map Rn to Rm, such that this difference quotient, where now everything is kind of vector valued, goes to 0, but we take norms of the numerator and the denominator individually. Okay, so this norm is a norm in Rm, and this norm is a norm in Rn. As I said, the numerator lives in Rm, the output space, and then the denominator h lives in Rn, the input space. And I'm putting little vector symbols on all my a's and h's to show that they are actually vectors. I might drop that in a little bit, but just to emphasize that they are vectors. Oh, and here are the notes, right? This is exactly what I said. These two things are in Rn. These two things in the numerator are in Rm. Yeah. Okay, and then for some notation, we denote this linear map by df at a, okay, or df evaluated at a, or maybe sometimes a little d, they're all the same, but something like derivative of f. Okay, and so this is establishing that the derivative of f is more officially or more correctly a linear map from one vector space to another. Okay, and it kind of has to match the dimensions of the original function. Okay. It's worth noting that if derivatives are kind of local objects, so if we could have started with f as a map from some region inside of Rn, and maybe it's Rm valued still, right? So maybe it's just some, like maybe omega here is just some open ball, right? So, or some open region inside of Rn. You can still define a function on like a part of Rn, right? And then you can say that, oh, let's say this thing is differentiable just on this small region. But then the derivative of f should still be a linear map from Rn. So the derivative at a, so I'll put a little a here. It should be a map from all of Rn to all of Rn. Okay, it's still a linear map, so it's defined on the entire vector space. But a is now this point inside of omega. So you're taking the derivative at some point. But this thing always stays the same. Okay. Meaning it's not defined on just omega anymore. It's defined on the entire vector space. Okay. So this is like a what if situation. If f was defined on some region, you would still have the derivative of f defined on the entire space Rn. Let's see. Okay, so here's maybe another important note about the way about the way this notation works. So this linear map I'm calling df of a. Okay, but df of a is itself a function from Rn to Rn. Okay, so a is not the input of this linear function here. I've already plugged in a into this. I've already plugged in a into this function, right? Or into this kind of expression. But now I end up with a linear map, right? So what I plug in is h, right? It makes sense to say plug in h, this vector, into this linear map df a of h. Okay, so this is all like one thing, sort of. Right, and this is my lambda of h, right? Lambda of h. Okay, but if you were to change the value a, right? A is like where you are taking the derivative. Okay, it has nothing to do with the linear map that you get out, or like plugging in. Sorry, it's not that it has nothing to do with it. It has nothing to do with the input of the linear map that you get out, right? But what if you change the value of a? What happens is you change the linear map itself. So you get, it's like you have a matrix where all the entries depend on a itself. Okay, but the matrix is a linear transformation of these column vectors. But all the entries of the matrix will change if you change what the value of a is. Okay. Okay, and then just a little bit more notation. df of a is a linear map from Rn to Rm. We talked about linear maps last time. And then if we express things in the standard basis of Rn and Rm, then we get an m by n matrix representation of the derivative at a. And this is called the Jacobian matrix of it. Okay, so maybe this is something familiar, or at least the name is familiar. You don't, but it's just the matrix that represents the derivatives. Okay, any questions so far? Cool, let's look at just a few examples stuff. Let's see, okay. I actually wanted a little more space for some other examples, so let me just put in one more page here. Okay, here's just some like first two examples, and we'll kind of see a pattern emerging, but I didn't really do the work to prove that these are the derivatives, but here are some functions and their derivatives, right? So here's a function that's defined on R2 and it's just scalar valued. So you plug in x and y and it just does sine x. There's no dependence on y, right? So, and then we let a, b be some point in R2 and I want to take the derivative at the point a, b. And I claim the derivative at the point a, b is the linear function that if I plug in hx and hy, I get cosine of a times hx. Okay. So the way, see, I put all the work goes into proving that this is true, but I'm just claiming it's true here. But I claim if I put this linear function into that limit definition, right, I should end up with that limit going to 0, which is like what I want, right? And no other function will work other than this one. Okay, that's also another theorem, is that the derivative is this unique linear transformation. There's only one derivative. Okay, but putting this in matrix form, you can write this as cosine of a times 0, right, times hx, there's this hx, hy vector. Okay. So maybe you can see how this works already. Here's another example if you want to confirm how this matrix is formed, right? But I claim the derivative of this new function, e to the x plus 2y, is given by this expression right here. And in matrix form, it's given by this matrix, right? I'm putting also the column vector because I'm in this equality, I'm also plugging in the input to the linear transformation, right? But the derivative itself is just this matrix. This is the derivative. Okay, I want to just make sure we understand this one thing about like inputs to the derivative versus this input, like they're two different inputs. So, okay. Yeah, no, I think I don't. Maybe I shouldn't just improvise an example right now. But if I come up with something later, I might send it. I might just attach it to the notes and send it. But or do we have any questions about this derivative so far? So we're going to actually go into computing this thing a little bit, but I'm just claiming like this is what it should look like. It should look like a matrix. This is the actual way of doing a derivative in multiple variables. Okay. Okay, so to compute this, right, maybe you can see how this is kind of working. We have a sine and we got a cosine and we got a 0 here, right? If we remember our things with partial derivatives, this is exactly what's going on. So the entries of the matrix will end up being the partial derivatives of the function, right? So we're going to get to that, but first I'm going to define partial derivatives just like in a more natural way of just what is the partial derivative of a function. So let's say we have a function that has a multivariable function, and let's just say we have one input, and this is just to keep things simpler so we don't have multiple outputs to keep track of. Let's just do a scalar valued multivariable function. Okay. So it has multiple inputs and one output. And let a be some point inside of Rn. Then we can define the partial derivative with respect to a fixed variable xi to be the single variable derivative of this function at t equals 0. Okay, so this function is you plug in t and just vary the ith variable, right? And so you fixed all the variables except for the ith variable, and this ith variable is the only variable you have left over. And so you take the derivative with respect to t, and you write this as the partial derivative of f with respect to xi at the point A is just the ordinary derivative of this variable where you fix everything else, right? And so this is maybe familiar with like how we compute them. When we do partial derivatives, we fix all the other variables and just take the derivative of one with respect to one variable, right? And here's the kind of the picture. This is taken right from Spivak. But this kind of graph right here is the graph of the scalar function capital F. Right, so this is f of x comma y here. This point right here is my point that I'm taking the derivative at. F of a comma b. And it's like, okay, this is x, this is y. And it looks like I'm taking the derivative in the x direction and I'm fixing y, right? So what I did was I considered this new function g of t to be f of a plus t b. Okay, and what this does is you're restricting to just this slice along the y equals b slice of the domain, right? So this line is maybe the y equals b line, right? And then I'm moving along this line, and then I'm looking at just this function. So this blue curve right here should be the graph of g of t. Right? And then when I take the ordinary derivative, I just get this number that represents the slope of this tangent line. G prime is 0. And that should be the derivative right here. That's what I'm defining the partial derivative to be, right? So you take these slices of the graph and you see what does the tangent look like on that slice. Okay. So then once you define partial derivatives in this way, right? This is maybe a natural way to do partial derivatives, is you fix all the variables and just you vary one variable only. Now I want to relate it to how that's what goes into the derivative matrix from before. Okay. So just a quick note. So we worked with just scalar valued functions, and now going up to vector valued functions. If we have a vector valued function, we can decompose f into its different vector components, right? So the output is an m vector. So this is maybe the output after you plug in x1 and xn, x1 through xn. You get these m different component functions, and these component functions are all scalar valued. Right? Putting them together into one big vector gives you this vector valued function. Right? So this is just like a thing about these vector valued functions. Just some other notation, this is maybe just like a totally separate point. If the coordinates on Rn are xi and the coordinates on Rm are yj, then we sometimes write the function f as just like y as depending on the x variables. Okay, so you might see this, I think, especially if we are working with later, when you're working with two different manifolds, you have like charts on two different manifolds. The chart on this one has coordinates that have x's. The chart on this manifold will have coordinates that are y's. And the y's, if you have a map from one to the other, the y's will depend on x's. And so we just write this. Okay. I don't know what I was writing. This is not anything. Okay. That's just the thing. So this is how we go to now you have our vector valued functions, right? So here's the theorem that kind of says what it tells us how to compute these derivative matrices, right? So originally the derivative matrix, it's defined with this difference quotient limit, right? But in order to avoid doing that, we just want to compute some partial derivatives, which are much easier to compute. So if we have a function from Rn to Rm, this theorem says that the ijth entry of the Jacobian matrix is given by the partial derivative of a component of it, right? So maybe this is a much shorter way of writing what I have written here, but the ijth component of the derivative matrix, once we represent things in the standard basis of Rn and Rm, is just given by the partial derivative of the fi component with respect to xj. Right, where I rewrote this thing using all the indices so you could see where which index goes where. Right? So if we write them out in partial derivatives, this is maybe the statement. Right? This is the statement of the theorem. And so it can be kind of important to get like the ordering of this, right? Like the the index on the X has to change as you go across the row, single row. Okay, and then as you go down, you go to new, the different vector inputs, or sorry, the different vector outputs of the function, right? And this is as you go to the right, the input variable index changes. That can be kind of important to get right in some cases. Okay. But this is maybe the Jacobian matrix that we're more familiar with from calculus. Okay, but it is true that this DF matrix, or this DF linear transformation, is this abstract linear transformation defined using that difference quotient thing, right? So there is this sort of hands-off picture where you don't write things out in coordinates. But if you want to write things out in coordinates, then you get this sort of matrix with partial derivatives, and this is maybe computable, right? But it's important that we have definitions of things that are not in coordinates for this manifold. Okay, any questions about this? I know this is the last thing we're doing. Cool, so that's kind of the end. There's other stuff to look into. And I think all of Spivak chapter 2 is just a really good read if you're just about before taking the that manifolds class. Actually, I have it right here. You can see how small it is. This is the book, and it's like this thin, and this is the entire 5-chapter book, right? So very recommended. Also, there's like a PDF. I will actually just send you guys a PDF if you just want to read that. But the exercises are good in chapter 2. I recommend this. These two theorems, inverse function theorem, and implicit function theorem, can be kind of tricky to get on the first reading if you haven't seen them before, but they're pretty important theorems if you are going further into geometry and just using smooth functions anywhere actually is pretty important stuff. They may be also important like everywhere, but I think inverse function theorem is not too hard to learn, and implicit function theorem I've been trying to like get a good grasp of what it's actually trying to say for like many years. But maybe you can get it like immediately. I feel like it's just me that's having trouble with implicit function theorem. Okay, any last questions? This is the end of the multivariable calculus. I said it was going to be pretty short. Great. I will hit stop on the recording, and we can get out of here.